Hi, I'm Tyler Singer Clark, and I'm a PhD student doing research in the neuroprosthetics lab at UC Davis. My undergraduate degree is actually in computer science, but I have since pivoted to biomedical engineering ever since I learned about this incredible work being done to help people with paralysis through the use of medical devices called brain-computer interfaces. A brain-computer interface is something which can read someone's brain activity and then figure out what movements they're trying to do or what words they're trying to say, even if they're unable to move their muscles or move their mouth. A brain-computer interface is super impactful for someone with ALS or brainstem stroke who is fully paralyzed and has to communicate through eye movements or blinking, or may even be unable to communicate at all, a condition also known as locked-in syndrome. Using a brain-computer interface, they can simply think about forming words with their mouth, and those words show up on a screen. As an assistive device, this is life-changing. You can interact with people again, with your family. You can ask for basic things you need, like tell a caregiver if you're in pain and you need them to adjust how you're positioned in your wheelchair. At the UC Davis Neuroprosthetics Lab, we're involved in a clinical trial called BrainGate, which lets us work directly with clinical trial participants with paralysis. Participants actually get surgery and they receive tiny little sensors in their brain, specifically in their motor cortex, which is a part of the brain concerned with movements. It's the neuroactivity recorded by these sensors that enable the brain-computer interface to figure out what movements they're thinking about. Our lab mostly cares about movements of the tongue and lips and things involved in speech, so our sensors go in a very particular part of the motor cortex concerned with speech movements. However, we've found that this part of the brain also contains information about directional movements the user is attempting. So now if the user thinks about moving their hand right and left, or up or down, our brain-computer interface enables them to control a computer cursor, for example, which of course unlocks a huge new set of capabilities for that person, in addition to speech. This is not the first cursor control by someone with paralysis, but it is the first time that it's been done from this area of the brain typically associated with speech movements. What we're so excited about is that this suggests we can give someone a single brain-computer interface that enables multiple types of functionality for them, not just speech or just computer control. And I think that's an important step toward the next generation of brain-computer interfaces that really improve the lives of people with paralysis.